Let's first look at an example where we analytically can solve an ordinary differential equation. So here we have our ordinary differential equation, x dot, or the derivative of x with respect to t, plus 2x equals 0. And here we have the initial condition that x of 0 is 5. So when time is 0, the value of x is 5. Our goal here is to find what is x of t that satisfies our ordinary differential equation that we have presented here. Now you cover this in differential equations class, but I'll go through quickly in this example how we could solve for what is the x of t value that solves this. So the first thing I want to do is I can rewrite my equation in terms of, instead of writing it as x dot, I'll write it as dx dt plus 2x equals 0. I'll drop that of t because we know that x is our dependent variable and t is our independent variable. An ordinary differential equation has only one independent variable, in this case t, and it may have multiple dependent variables and their derivatives. In this case, our dependent variable is x, and we also have its derivative, dx dt, or x dot. I can move the 2x to the right-hand side, so I have dx dt is equal to 2 times x. And what I can do here is I can multiply by dt. Now, mathematically, this isn't the most correct thing to do. You can't really multiply by the dt term, but it works equivalently in our solution. So I multiplied through by dt, and I divide by x. So if you've taken the differential equations class, what we see we've done here, it's separable. The left-hand side has only x terms in it, and the right-hand side has only t terms, and it has a constant term. But what this allows us to do is now I can take my left-hand side, I can take my right-hand side, and I can integrate both of them. The left-hand side, I want to integrate 1 over x dx, or 1 over x with respect to dx, and the right-hand side, I want to integrate negative 2 dt. On the right-hand side, I can pull that negative 2 out if I want, and we know how to take the integral of the left-hand side and of the right-hand side. So of the left-hand side, the integral of 1 over x is going to be natural log of x. And these are indefinite integrals, so when we integrate the right-hand side, we're going to get negative 2 times t, and then I'm going to choose to put that c term on the right-hand side here. So left-hand side natural log x equals negative 2t plus c. Remember, what we're ultimately interested here in any of these cases is we want to know what is x of t. So I need to solve this now for x. Right now I have log x on the left-hand side, so what I can do is I can put both the right-hand side and the left-hand side as powers of e. So if I raise e to the log x, I just get x. That's my left-hand side. On the right-hand side, e to the negative 2t plus c. I can rewrite using exponential rules that that's going to be the same as e to the negative 2t times e to the c. Because if I have like bases and I'm multiplying them together, I can add their exponents. And then that term, I can rewrite e to the c. C is a constant term, e is a constant term. I can just rewrite that as c1. So solving this, I have x is equal to c1 times e to the negative 2t. So again, my goal is I want x in terms of t. But right now, what I don't know is what is the value of my constant value c1. And this is where I can use my initial condition that x of 0 is equal to 5. So since I have an expression for x now, I can plug in the value 0 for t, and I know that the value of x at that time should be equal to 5. So rewriting this, I know 5 is equal to c1 times e to the negative 2 times 0, which is just 0. E to the 0 is just 1. So solving this, I know that c1 must be equal to 5. So finally, I can rewrite this entire thing, and I have x of t is going to be equal to 5 times e to the negative 2t. And that is my solution to this differential equation. And we could check this if we wanted to. If I took 5 e to the negative 2t, first of all, it satisfies that initial condition. Remember, if I plug in 0, that expression is equal to 5. And if I take this expression, I put it back into my equation, so I take its time derivative plus 2 times its value, I will get 0 as my answer. So in this case, analytically, because it was separable, I had a method to analytically solve for x of t and include the initial condition in my solution.